Your relatives appear in the slide.
Okay, we can start. Yes. Okay, welcome everyone. So it's a pleasure to have Krishna S as the speaker today. So Krishna works on automata, logic, and various applications of following methods. So Krishna is faculty member at IIT Bombay, and I know her since a long time. When I was a PhD student, and I visited her quite often, like almost every year, once or twice, I used to come to IIT Bombay and visit her. And I'm very happy that she is in the effort today after several years. She also used to visit the effort for 24 stores here. And so today she is going to talk about verification of concurrent programs. So good.
Thanks. Thank you, Shibashish, for the invitation and this opportunity to talk. Okay, so the title today is verification of concurrent programs and the release acquired. So let's not worry about the last two terms, release acquired. We soon found out what that is. So I'll begin by just saying concurrency is everywhere. So that's like a motivation. So I also have some pictures just to state why I'm saying this. Okay. So let's think about the lowest level of system design, which is basically on the chip level, right? So all the multi-core architectures. So look at all the leading manufacturers like Intel, ARM, IBM. They all have multi-core architectures. We no longer have single-core architecture. So that's one instance of concurrency at the lowest level. Okay, now if I move ahead to, let's say, the highest level of system design, like in distributed databases, these are called the geospatial things, right? Like servers distributed across the world. Like, for instance, if I think of Facebook, like if I like a post of a friend, it's like propagated everywhere in a consistent way. So that is again an instance of concurrency happening. And, but okay, this is just advertisement. What I'm really going to talk about, the instance of concurrency I'm going to talk about is none of this actually. So there is this recent trend called weak memory models, which is basically to incorporate the style of these architectures, the recent memory architectures. So the recent programming language development like C11 and Java have now developed some primitives which can take into consideration these weak memory models. And that is where the term release and acquire basically features. So they have things called release writes and acquire reads. So these are part of the latest C11 memory model. So what I'll be talking about is really analysis of concurrent programs which have these kind of primitives. So that is a real talk. But okay, till we get there, we'll first see what concurrent programs look like. And we'll first see them interpreted under the model which all of us know, which is sequential consistency. Okay, so a concurrent program looks like this. So SC means sequential consistency. So sequential consistency is a standard interpretation for concurrent programs. So in this example that you see here, I have two threads, th1, th2. There is one shared variable called x, and A and B are local variables or local registers. So, okay, so I call this a process or a thread interchangeably. And a write operation looks like this. So x assigns the value 1, the value 2. And this is a read operation. I'm reading from x into the local variable A and into the local variable B. That's a read operation. And let's see what else I've got. So in execution, I have a sample execution here. So I'm here in this particular execution, I'm executing the thread 1. I'm writing 1 to x. I'm reading 1 from x. So A gets the value 1. And then so typically the way in which your program will execute is you have to respect the order in which instructions appear in each thread. So that is called the program order. But across threads, you can interleave them in any way you want, right? And the rule basically is that you have to always read from the last value written from any variable that you're trying to read. So that is basically the rule for sequential consistency. So this is a sample execution. There are of course other possible executions too. I need not have done thread 1 followed by thread 2. I could have just interleaved them in various possible ways. And now after executing such a program, I want to ask whether a certain assertion holds good. So this could be a safety property, essentially a violation of a safety property I'm trying to check. So the question I'm really asking is, does this program have an execution where I will see this getting witnessed? Okay, do I witness this particular assertion holding? This is the property I'm trying to access. Okay, so now before we get into executions, I'm just going to represent what is called a trace. I don't need it too much for this talk, but it's good to have it. So a trace is basically an abstract way of capturing a concrete execution. So a trace is nothing but a graph at the end of the day. And the reason why traces are preferred over concrete executions is because a trace can capture multiple executions. Okay, so in some sense, if I want to build a model checker for checking a concurrent program, where I have to explore all possible executions, I'm actually better off if I just look at the traces corresponding to them than the actual concrete executions. Okay? So just to kind of show what a trace is, so first what I do is, okay, this is easy, right? Whatever events are there in each thread, I just draw them. And the PO basically represents program order, so that cannot be changed. And in this case, I am reading from the right XS1 into A sec. So RF means read from. So the reads from edge is dynamically decided based on the actual execution. So in this particular execution, the RF edges are between the right of XS1 to AS1 and respectively on this side too. So this is also part of my graph, but this gets synthesized dynamically depending on the execution. PO never changes, of course. And then another thing I have is something called a coherence order. So the coherence order is basically the order in which writes happen to every location or variable, whatever term you are comfortable with. So in this execution, if you see the one above, I first wrote 1 to x and then I wrote 2 to x, right? So in some sense, xs1 is ahead in the coherence order than xs2. So that's why the CO arrow goes from xs1 to xs2. This again is something that dynamically depends on the execution. And finally, I have one more edge called, okay, so this is a total order per variable. CO is a total order because take any two writes to the same variable, I can always find the order between them. So that's a total order. And finally, I have something called a from reads. So what is a from reads? So if you look at this example, okay, A read the value of x to be 1, and then the value it read from was overwritten by this write x is 2. Okay. So from reads basically is going from a read to that write which overwrote the value it read. Okay, that's a from read. Okay, reads to writes. Anyway, so now this graph represents this execution. Now, if I ignore the CO edge, it can represent many more executions possibly. Okay, that is what we will say later on. But now to say that this execution is consistent or it's a proper sequentially consistent execution, I just have to say that the graph you form, whatever it is acyclic with respect to all these events. This is all the condition to check for consistency and sequential consistency. So in some sense, if you read from not the latest value written, then your RF and FR combination will give you a cycle. And that basically says that this is not a consistent execution for the sequential consistency model. Okay? So that is how we say it is consistent with respect to sequential consistency. So this, for example, is a good execution because it has read from the latest value written, and then I don't find any cycle, so this is good.
So just to make sure that I'm following correctly, so that RF can be across threads also, right?
Absolutely. Yeah. In this example, it so happens that I'm reading from the same thread. RF can go across threads, and FR can also go across threads. I think that was already here in this case. It was already across threads. Okay, so now I'm just going to say that if I look at these two executions, they are both represented by the same trace, right? Because it doesn't matter the value in which I am assigning these to an AS2, even if they are happening in the other way around, as it happens in another execution, the same trace captures both of them. So this just to kind of touch upon the fact that traces actually save a lot of effort than actually working with concrete executions. Let's work with abstract executions, your traces. Okay, so now that is some introduction about concurrent programs, traces, and abstract executions. Now what I'm going to do is, before we get to the release acquire model, I'm just going to look at some examples of concurrent programs. I'm going to ask whether this particular specification written here is possible under sequential consistency. And then I'll tell you whether this was possible under the release acquire model. So I'll introduce it later, but first we'll get familiar with it by looking at examples and inferring what could be release acquire and how it is different from sequential consistency. Okay, so let's see this. So I have one process. So it is called, so all the examples I'm showing here are so-called litmus tests. So litmus tests are basically small programs created, which basically help you test whether, if you build a tool, for example, it will help you to test whether the tool you built is behaving appropriately. Okay, so litmus tests, there are like several thousands of litmus tests available. And the test, all the examples I have are standard litmus tests. So this is an example called message passing. It is called so for a reason. We'll see why. So anyway, here I have two variables x and y, two threads, whatever colors are there. So the question is, so x and y are shared variables. Rx is the name of a local variable here. The question I'm going to ask is it possible to get Rx to be 0? In other words, can Rx read the value 0 from x? If I were to execute under sequential consistency, it will not be possible because, okay, so notice that to reach here, I have to basically come through the while loop. And to enter through the while loop, I need to see a value other than 0, right? Because until y is 0, I'm just going to say skip. So the moment y is not becoming 0, I will come below. So for that to happen, this must have been executed. But then for this to have been executed, this must have been executed. So which means that under sequential consistency, because I always read the last value written, this value read should be 1, not 0. Okay. So now under release acquired, which is a new paradigm which we will see soon, also this is not possible. Okay, and I tell you the reason. So the main difference between sequential consistency and release acquired is the following. So sequential consistency is perhaps the model which has the most amount of synchronization among threads. The most synchronization because anyone who writes a value is like propagated immediately to everybody else, whether or not they're interested in it, you have to know. Right? It's like a news item appeared in the newspaper, everybody has to know it immediately. It's something like that. Under release acquire, the synchronization happens only between reads and writes. So that's why the release writes and acquire reads. So in some sense, if there is a RF happening between two guys, then that is a form of synchronization and release. So if you look at this example, so clearly when this while loop breaks, I have RFX from this write to this read. So basically that means this process has conveyed whatever it knows at this point of time to this thread, which means it has passed a message that x was 1 also, right? So in some sense, the synchronization happens like this. So when this y equal to 2 is read, it's also knowing the fact that x has become 1, therefore this guy cannot read 0 under reason. So it's not because it has to read the latest value, it's because it became aware of a write and therefore it cannot ignore the latest value it is aware of and it cannot go back in time in reason. Okay, let's see. I have more examples, so hopefully it becomes clearer. Here's another example called a store buffer. Again, two variables x and y. I am writing x is 1, writing y is 1. I am reading from y to ry, reading from x to rx. I am asking, can you get both rx and ry to be 0? Under sequential consistency, the answer is no, of course not, because, well, okay, I can get one of them to be 0 is possible, but not both of them to be 0. The reason being, okay, let me assume I execute x is 1 first. Now, if I want to read from y, I can read 0. That's possible. Likewise, had I started y equal to 1, and if I wanted to read, I could have read the value 0. So one of them can be 0, but both cannot be 0 under sequential consistency. Now, let's think about release acquire. So remember in release acquire, the synchronization happens only between a write and a corresponding read. That's the only way that threads talk between each other. So now, okay, this guy wrote x is 1, let's say, and this guy wrote y equal to 1, let's say. Now notice that there is no communication between the threads, right? There is no RF established already, so that by the time I come here, this guy became aware of this write. This guy is not aware of that. So in release acquire, when I come here, I can read 0. I could have also read it. Okay, so in some sense, when the write is finished in the memory at this point of time, this guy says, I see two values available for me to read from. One is y is 0 and one is y is 1. Okay, I could have read y is 1, but I can also read y is 0. The same reasoning applies here because they have not talked to each other. At this point, he could have read 0 or 1. So in particular, this behavior is possible under release acquire, which is an extra behavior which was not possible under sequential consistency.
Quite confused by this. So is it also equivalent to think that processors have local variables named x and y, and these are not global?
Okay, so
what would be the difference between that and the model that you have in mind?
So to answer the question in a way that is like close to release acquire, the main difference is under sequential consistency, everybody has the same view of the world. Under release acquire, I may have a certain value for the global variables. If you are a different process, the values that you may be aware of for the same variables need not be what my views.
So so if I said that variable, the thing that I call X is local to me, and the thing that guy calls Y is.
So
what
really
is the
speaking, the
difference?
local variables is just Ry and Rx,
Yeah,
right? X and Y are still global or shared variables, they're shared across processes. It is just that when I come here, the values I see for Y, even if I am assuming both writes have been done, when I come here, this guy can see two values for Y in the memory, global memory, 0 and 1.
he can see two meaning.
So, okay, let me put it this way, right? So, okay, so imagine there is a timeline. When events happen, there is a timeline, okay? So when this is done, I'm going to say publish in the newspaper, okay? X is 1 is written, and I publish this also in the newspaper. But nobody called me and told me, hey, X has been 1, okay? Nobody called me and told me. Now when I come here, okay, if I wanted to check the newspaper, I would have been aware that after the initial value of 0, somebody actually wrote Y to be 1. But nobody has come and told me yet, right? So I'm free to ignore it. And the initial value is available for me to read.
So I have a local copy of the variable.
I wouldn't call it a local copy, it's a view.
No,
Local
but
view.
I can choose to refresh that local copy,
Exactly.
synchronize it with the global one,
Exactly.
or I may choose not to.
Exactly.
That's what.
Exactly. So in some sense, okay, let's wait for, I have more examples. Hopefully this becomes clear.
But inside the program construct, is there a way to say that explicitly that, hey, refresh my?
No.
So then it's up to the system to give you the view that you, I mean.
Then maybe that will come.
So we have a formal operational semantics which will come. Okay, and to answer your question about this, so if you remember a few slides back, I showed this trace, right? With an acyclic condition for sequential consistency. So those are actually the axioms of sequential consistency. We have some axioms to release acquire too, which allow some form of cycles and which disallow some form of cycles. So if you want to exactly follow the rule, what is allowed under RA, what is not allowed under RA, you can either go with that graph model saying these cycles are forbidden, these cycles are allowed, or I'm not going to present the axiomatic semantics today. I'll talk about the operational semantics where I'll associate timestamps and use the notion of recency. Okay, so hopefully another couple of examples and with the formal semantics things should become clear, but I see your point. So maybe at this point of time, it's okay to say that we have a local copy of the variable because in some sense it is a bit like that. It's like I have a local view as opposed to a global memory pool out there.
So just one quick question over here. Okay, suppose there was a process 3 which said y is equal to 2 and rx equals x. Then process 1 would actually have 3 options for y.
Absolutely, that's correct. Yeah, perfect. Okay, so let's go ahead with the third example. Again, I have two processes, but only a single variable now. I have only one shared variable x. A is local. Oops, sorry. A is local and B is local. So I'm asking, is it possible to achieve A is 2 and B is 1? So let's see. So if I'm working under sequential consistency, so I write x is 1. Okay, because, so let me say I want to fulfill A is 2. Okay, that is what I want to fulfill. I would say, okay, I execute x is 1, but that's not what I want to read. So I'll make this guy happen. And then I will say A is 2. But then the moment that happens, then I can't get base 1 under sequential consistency, right? Because 1 is no longer the latest value written. Now, if you think under release acquire 2, okay, now we are thinking about this recency, timestamps, these kind of stuff. Once again, so here, okay, x is 1 is written, it's written by the same thread. So when I come here, I'm aware that I cannot read 0. This much I'm aware. The initial value was 0. I can't read 0. That much is clear because I myself know of a later write. So at this point, I can read 1, certainly. Now let's say that this write also happened. So now when I come here, I have now somehow two choices to make. Depending on the recency between these two guys, I can read either one or two. So if I want to read 2, I am going to say this has a later timestamp than this one, or this happened later in the timeline than this guy happened, the global timeline. And keeping that in mind, I am going to allow A's to be 2. But the moment I do that, when I come here, now in the global timeline for X, I am saying X is 1 is behind X is 2. So somehow I cannot permit B to be 1. So even in the release acquired, I cannot see this behavior. So this is an example where the answer is no and no under sequential consistency and release. Both are no. Okay, so
So can you just go back to the previous example, the previous one?
here variables are different.
Yeah.
Okay, here's another example, 4 processes. Okay. I want to ask whether A is 1 and B is 0 and all these guys can hold together. So first sequential consistency. Okay, let's see. I want this to happen. Let's say if I want to make this happen, I'll say, okay, write X is 1. I can of course then say A is 1. If I do not do this yet, I can read B is 0. So this combination is possible so far. And then I want this to happen, so I'll make Y to be 1 and then I can read this, but then I can't do this to be 0. The sequential consistency, if I manage all the 3 of these guys, then this is not possible. Okay, release acquired. Once again, if I want A is 1, I would make this right. I put a reads from, right? So this guy is aware of this right. So very good. Now when I come here, okay, let me also write this, right? Let me write this, doesn't matter. So the release acquired execution, I'm saying I wrote this, I read this. This guy wrote it, but they are not talking to each other somehow. So when I come here, this guy is aware that there was a data right in the global memory, but he has 2 choices, 0 or 1. He chooses to read 0 here. Okay, when I come here, okay, I want to read Y equal to 1. Very good. So these guys are talking and these guys are talking, right? There is no crosstalk happening between other threads. So this guy is, kind of ready from here. But then, okay, he's not aware. He's not, obliged to read this one. So he can read 0. Basically. So does it get clearer, the model a bit?
So far, it's still consistent with the local copy.
No, actually, it's not.
I think,
No, at some
personal
point,
view.
at some point, that guy chose to read the
No, for
global
example, so can you go back one slide? Here, this is not consistent with local
copy.
copy.
Why not?
Because if you have local copy.
No, with the local copy, with the idea of synchronizing it with the global one. Right?
Yeah, that is a difference. It's not just local copy.
Yeah.
Okay, this is my last example before we jump into the formal semantics. Okay, so this is called 2 threads in 2 lines.
Sorry, I have one other question. So, are each process is aware of the existence of other processes as well? Like, in programming, you can spawn a thread dynamically.
Yeah.
So, does that somehow make
No,
other threads aware?
no. So we don't, yeah, you can have that fork operation if you want, but in this model, so far, I don't have this facility of
So,
spawning a
but
thread.
then when you say I want to synchronize it with the global thing, so it's like each process says I want to synchronize this variable, and then there's some higher being which is synchronizing with every global thing.
Exactly. So
Not by that
there
variable.
is a global memory pool, right? Which is visible to everybody.
Right.
Everybody has their own local views. So their local view determines what they can read from the global thing. So like, for example, if I read the paper of 2 days back, then I cannot, pick from the memory pool an item which was 5 days ago. I can't do that. But now I have the choice of reading yesterday's paper or today's paper because my timeline stands 2 days back.
And once I commit to the global view, in a later operation in that same thread, I cannot now read my all memory is gone, right? I cannot say now I revert back to my own view. That's not possible.
No. Once you synchronize, you come up to a timeline and then you have to only go ahead.
Yeah.
So every now and then you open your window.
Exactly.
Decide to look out of the window.
Then you flush out your all your
You don't get to.
Each thread has like a cache or something and then.
Yeah. View cache is a various. Okay, what do you think of this example? So can I get A is 1 and B is 1? So anyway, I'm writing X is 1, Y is 2, Y is 1, X is 2. So this guy, okay, let me say I want to fulfill this guy's A is 1 wish, which means, okay, I put a RF from here. And if I do that, under sequential consistency at least, okay, so which means I'm done with this, then I have done this. So then can I get B is 1?
sequential you cannot, right?
Exactly. Sequential consistency you cannot. But now let's go to this release acquire model. Okay. So let's see, right? So anyway, I want to fulfill ACE1, so which means I'm establishing a synchronization from this thread here. Okay, so this guy is going to be ACE1. Now, when this happens, somehow this guy is aware of this write. That's all. And now when I come here to read B, so when I come here, I'm aware of this write, but this is also a write that is possible. So somehow, in my recency timeline, if I decide that XS1 is ordered later than XS2, while YS1 is ordered later than YS2. So notice there's a cycle happening literally, okay? So it's like I'm drawing a CO edge like this, and from 2 to 1, right? So 2 to 1, program order, 2 to 1, come back here. I'm actually getting a cycle here. But release acquire permits this cycle. Sequential consistency does not permit this cycle. So this allowed under release. So in some sense, yeah, this local cache view, these are terms which will align to this formal semantics. I think I'm done with all the examples. We can go to the formal model, but okay, I'm just setting up the question that in general, the question that we are interested in is asking this. I'm given some concurrent program, I'm given some assertion, which is typically a violation. And I'm going to ask, does there exist an execution witnessing the violation? And if you look at existing techniques, right, predominantly, if you look at knowledge checkers, what they do is something called dynamic partial order reduction algorithm, where they explore all possible traces, not the content executions, but the abstract executions. And then they check, okay, does my given trace have it already witnessed the violation? So one more thing I must say about the deep OR algorithms are that, so these are not really complete techniques, these are approximate techniques. In the sense, if your program has loops in it, then I actually am going to set a bound for opening up the loop, so that the program now becomes a finite object. And then I can now do my trace execution. And clearly, because I'm not checking every complete execution, but like equivalence classes of complete executions, typically the number of traces I have to check is much lesser than the actual abstract the complete executions. And this is how all the model checkers, okay, the deep OR algorithms work in this way. Now, depending on how many edges you want to have or not have, it becomes that much faster. Okay, so this is like the state of the art. And now let's look at the formal semantics for release acquire. So just to give a picture about how does sequential consistency look like, there is a global memory and everybody is talking to that memory. That's how everybody synchronizes. It's like everybody looks at the same object, everybody is up to it. Okay, that is sequential consistency. Now let's look at release acquire. So in release acquire, I have a global memory pool. So here I'm assuming I have two variables called x and y. So this top component represents the value that was written to the variable x. And these represent some timestamps at the time the write happened to the particular variable. Okay, so this bottom thing is called a vector clock or a component of timestamps, whichever way you want to talk about it. So this is a memory pool and it's a pool of views. Okay, so each of these blocks can also be called a view. That's a name for that. So each such view is created when a write operation happens. Okay, and then these two things are called logical clocks for x, logical clocks for y. Because I have only two variables, where n variables, this bottom thing will be of length n. Right. So now let's actually see an example. So this is suppose the pool looks like this at some point of time, and I'm trying to read a value from x into the local variable a, and assume that this is my local view. Okay, so this is basically timestamps. So this guy is timestamp for x is 3, timestamp for y is 2. Okay, which means that is what he is aware of in the global timeline of what happened to x, what happened to y. So now if I want to say I want to read from x, I'm just going to do the following. You select some view in the memory which is pertaining to x. Okay, so I am not concerned about the y views, let me forget about them. So there are two views of x in the memory pool, and I can take any of them whose timestamp of x is at least as large as your current timestamp of x. I am not worried about the timestamp of y at all here. So my timestamp of x is 3. So here this guy happened later than me. This guy happened before, just like some old thing. So I can only read this particular message corresponding to x. This is kind of obsolete for me. So then I'm going to choose that guy, okay, the x is 1. And then I'm just going to take that value and I'll do something called merging my view with the view I'm picking from the memory pool. So when I merge my view, okay, my knowledge about x has increased. My knowledge about y was ahead of what this guy knew. I'll keep my ahead knowledge. I will not go back. Okay, so the view is updated to 4 and 2 now. And the value that a gets happens to be 1. And that's what happens. Okay, so now, small dab. So anyway, so that was a read operation that happened to A is X. So now let's look at how does a write operation behave. So now I want to write the value 2 to X, so it's a write operation. My local view is now 4 and 2. So here's what I do. I can now create a new local view because I'm advancing in time, right? I'm writing a new value, so I advance my local view. So I can pick a timestamp corresponding to X, which is higher than my, whatever I know, I have to pick something higher. And I also take care that the value I choose is already not there in the memory pool in existence. Okay, that is something I do. And then I create a new copy, I create a new view, put it in the memory pool, so that now if somebody else wants to read from X, they can also decide whether they want to read the value I have written to X. Okay, so let's see. So the current view timestamp is 4. So I can create a new view which looks like 5 and 2 other timestamps. Notice that I have not changed the timestamp of Y, it remains what it was. And now I want to add this thing into the memory pool. Okay, copy the new view to the memory. So the memory pool is expanded with 1 extra write. And that's about it. So every time a write happens, the memory pool is expanding, creating potentially new views for people to read from. Now the last one is again a read from the variable Y. Okay, so now if I want to choose that, how do I do? So my current timestamp for Y happens to be 2. So the possibilities here are this guy is obsolete because the timestamp is 0, this guy is higher, so this is the only choice for me. So when I do that, the value of B becomes 5 and my local view becomes 5 and 7 because I'm merging those. So now just to kind of, I'm going to revisit 2 examples we saw before with this proper semantics and see, okay, what we said before, is it really correct? Okay. So remember store buffer, we said it is possible under any subquery to get Rx and Ry both to be 0. So this is my memory pool. This is my local view, X and Y are both 0 to begin with, the timestamp is 0 and 0 respectively. So let's see, I'm executing X is 1. So I created a new view in the memory pool, right? And my local view has now become 3 and 0. So it agrees with what is entered the memory pool. Now I am executing Y is 1. That means I have chosen timestamp 7 for Y. So fine, that's a new thing in the memory pool. So now clearly, when I am trying to read from Y, my current timestamp is 0. I have 2 candidates in the memory pool to read from. I could have read from either of them. So let me choose to read from this guy. That is why I can get Ry 0. Same explanation holds for getting Rx 0. Right? So the choice of timestamp just enables me to read not necessarily the last value that was written globally. But it's like saying I can do anything which is beyond my current time, right? That may not be the latest news available in the world. Okay, so one more example and then actually can
I mean, it will be equal to my current time.
Yes. So this is basically to say I can read my own write, right? I must be permitted to do that. That is why greater than or equal to what I do. Okay, so this was the 2 plus 2W example. Once again, I have whatever the initial memory pool has these things, the 0, 0 are the timestamps. So let's see what happens. So I'm executing X is 1. I created this message in the memory pool. Now I am writing Y is 2. So when I do that, what happens? Oh, sorry, I did execute Y is 2. I executed Y is 1. Sorry, the second thread. So now this is the message I have. Okay. And now let me do Y. Okay, what am I doing now? I'm executing Y is 2. Okay, which means my local view is changing to. So I made it 9, 1 as my timestamp. I have a new message in the memory pool. And I'm choosing X is 2. So I've chosen 5 elements. So notice here that the timestamp I'm choosing for this X is 2 is 5, which is actually smaller than what was chosen for X is 1. Even though, in the global timeline, it so happens that this was executed and then this was executed. I'm allowed to do that somehow because when this got executed, this guy's knowledge about X was actually 0. So he's allowed to pick 5, which is smaller than 9, even though globally everybody knew 9. Not everybody. Out there in the world, 9 was known. But this guy could have said, because he was not aware of that 9, he's allowed to choose 5. Which is why we are actually able to have this, I can read now, Y is 1, and I can read B is also 1, essentially. Are we good? Okay. So now I have just one more operation to describe, which I hid it all along. So a typical concurrent program has a read operation, a write operation. You have assignments to local variables, that is fine. Now there's something called an atomic read write or a compare and swap or read modify write. There's a various names of calling the same operation. So as the name says, an atomic read write is atomically doing a read followed by a write, which means there is no intervention by anybody between the read and the write happening. Now these are typical ways in which locks can be implemented. It is like saying, okay, I read a value and then I overwrite it with something else. Okay, so typically if you want to have a spin loop or something like that, you can implement it using an atomic read write. So I just want to present the semantics for atomic read write, and then we have seen the entire array semantics. Okay, so this is again an example. So this R is nothing but a local variable. Okay, so nothing happens in the memory. I am writing locally R is 1. Okay, nothing happens. Fine, I do that. Y is a shared variable. So when I write Y is 1, I do what I expect to do. I change my local view, I add a thing in the memory pool. R prime is again a local variable. So nothing happens in the memory pool, I do it locally. Fine. And now I come to the atomic read write. Okay, so when I come to the atomic read write, the way to read this is I'm going to check if I can read from X the value of R. And if I'm successful in doing so, I'm going to override the value of X with R prime, the value of R prime. Okay, so check if I can read X is equal to 1 from the memory pool. Can I do that? If I can do that, immediately override X with value R. So I'm trying to say, can I read this message from the memory pool? The answer is yes, because my timestamp is 0, this guy's timestamp is 3, so I can read it. So I do that. And then, okay, I immediately update my local view, but I don't stop there. I instantaneously write the value 2 to X with my new view being 47. So the point to note here is that the choice of timestamp goes from T to T plus 1 when I do an atomic read, right? So what this also kind of tells you is that if I have utilized this message to read from as part of an atomic read, right? Nobody else can now use the same message to read from in their atomic read write. Why? Because when I choose to read from this as part of my atomic read write, this timestamp became 4. If somebody else tries to do that, they will also be forced to put 4, which they can't because there's already 4 here. Right? The choice of timestamps I do. I just need to find my phone and shut it. It's coming at the wrong time. Because these guys talk to each other when I get the call, it comes in. Sorry about that. Because of synchronization. Oh, it won't happen again.
But it can happen that the 4, the timestamp 4 can be there, I mean, from some other process.
Oh, yeah. If that happens, then I will not be able to complete this successfully.
Okay.
Yeah, that's true. So likewise, right? Likewise, if I was unable to read this message, once again, I'm stuck. So that's typically how the lock works, right? So if I want to kind of access something, first of all, I must be able to get this value to be read from, and then I'm going to say, okay, now I take the lock. So if I can't even take the lock, I have to just keep waiting, right? I can keep waiting, hoping that sometime I'll be able to read XS1.
But you can take the lock as long as there is something which is a higher value, like as long as there is some timestamp which is a higher value.
Yeah, exactly. Yeah, that's right. So there are two things here. One, I must be able to read this guy, and then I must be able to put this in, so nobody else should have taken this timestamp. Yeah, that's awesome.
It's also possible that some other process could update R prime before this atomic read write.
No, R prime is a local.
R prime is a local.
Local variable. Yeah. So the syntax typically is like this is a shared variable. These are both local variables. Yeah. So that way it's in my control what I want for X and what I want for X to be 1. Okay, so we are done with the operational semantics of release acquire. I have one example to show. Maybe I think we have seen enough examples, so I can go through this quickly. Okay, this is just to say a typical array run. This is just to kind of show how the local view changes, how the global pool changes. Okay, so I'm reading value 0. I wrote 1, so my timestamp changed to 2. And now let's see what happens. I'm trying to read from Y. So, okay, this guy is chosen to read 1. He could have read 0, 2. Okay, then I'm writing X is 1. I'm writing X is 2. And now when this guy wants to read from X, he has 3 choices. He can read 0, 1, or 2. But I think he reads 2. Okay, fine. So this like just reinforcing what we've seen so far. So now with all that said, I will go to the main problem. So the problem we are trying to check is given a concurrent program under release acquire, can I check if it is going to have a safety violation? Right? This is the question that I'm interested in. So it says particular state reachable in a concurrent program under release acquire. Now, of course, so is it decidable? Is it undecidable? If it is decidable, what's the complexity? These are typical questions that we ask. And of course, now notice that each process I consider here is a finite state thing. So I'm going to assume it's a finite state process. Okay, it doesn't really matter, but here, at least for the main result I'm going to show, it doesn't matter. But for the later things, the finite state thing would matter a bit. Now, what do I know about this problem under sequential consistency? The reachability is known to be p-space complete. This is well known for sequential consistency. So for release acquire, this problem was open for a long time. So notice that it did not, affect really the development of model checkers or the deeper algorithms because anyway they were straightening the program up to a loop bound. So for them, none of this matters, right? Because anyway, it's like approximating it. So those techniques work.
So for these things, the input is the description of the program, and
Yes,
when you
that's
say
correct.
the description of the program,
And there's some
and some state.
exactly, some method. So that is the typical input, and you're supposed to check whether it's reachable. Okay, so anyway, so I was saying that even though the decidability for RA was open, we already had model checkers for RA, precisely because they were not, fully proper ones; they were approximate ones. But given that this problem was open, we delved into it, and this is what we have. Okay, the reachability problem is undecidable for release acquire, while for its sequential consistency, it is p-space complete. So I'm just going to run through the reduction. So the reduction follows from the PCP, post correspondence problem. I'm sure everybody knows it, but I have it in my slide just for completeness. Okay, so the PCP problem gives you two lists, right? And at each index of the lists have equal length, of course, and each position has some word. And I'm going to ask, give me the sequence of indices so that the corresponding words are the same. Right? This is the PCP problem. Okay, so now how do we do the reduction? So the reduction happens as follows. I am going to construct a concurrent program which has 4 processes, P1, P2, P3, P4. So the idea is pretty much the following. The idea is that so process P1 is a writer. Okay, so it's going to guess a sequence of indices and a sequence of letters from the first list. Okay, it is thinking that from the first list, this is what should make a solution. And the process P2 is also a writer. The process P2 does the same thing on the second list. Now,
so what do you mean by sequence of letters? If you have the indices already, if you guess, then you also get the letters.
Yeah, so for example, but then it's not enough to check the indices are same. I'm also trying to capture the actual word and checking the word for index. Okay. So in the reduction, you will see that when process P1 guesses, it is going to say, okay, suppose it guesses 2, 1, 4, right? So we're writing variables, the letters of this 2, 1, and 4. And this guy would have also done something. And I'm going to check if they actually wrote the same thing. That is what I'm going to pretty much. So it's like a read-write thing happening. With a twist, of course, which you will see. It's not just read and write. Read and write is not good enough. At least I don't know if it is good enough. Okay. So anyway, so P1 makes its own guess, P2 makes its own guess. So what I mean by this arrow.
The sequence of indices are what do you mean by sequence of letters?
So sequence of letters corresponding to those indices, right? So if I say position 1 ABA, let's say.
Okay.
So then I'm going to write A into variable, B into another variable.
Okay.
Like that, right? So it's basically just writing blindly the indices and the corresponding letters that made up those indices.
Okay.
And then P1 is done. But then somebody has to, and likewise Q2 will also be done. It does exactly the same thing, but then somebody has to verify that these guys are not cheating. Okay, so just to give a glimpse of what it could be like. So I've chosen these colors instead of letters. It's the same thing, of course. So what could have happened is, let's say P1 is like saying 1, 2, and 3. That's the guess it made, let's say. So it is using variables x1, x2 to alternately write the symbols of each position of the list it is kind of guessing. So suppose it said 1, 2, and 3 is what it did. So it writes okay, green is x1, then blue is x2, then green. So alternately write to two variables x1, x2, the symbols that come from these lists, and alternately write to variables y1, y2, the indices you have seen along the way. Okay, that is what P1 does. Now, of course, I don't think there's a correct solution in this example, but P2 would do something similar. Okay, this is what the string created by P1 looks like this, based on this indices it has chosen. P2, if it were to do the same thing, okay, if it were to do the same thing, then this is what I would get, and clearly they are not the same, but that's fine.
Sorry, I don't really able to follow this. How do you get those variables x1, x2, x1? How do you choose that order? Like first is x1, then is x2, and then x1.
I just create a loop, right? So I put a loop when I construct my program P1.
I see.
I would just say, okay, so there are like multiple variables.
I see.
I would say guess an index, right? So it gets the index I, and then this program P1 would look at UI. So I know what is the string at UI. I know that, right? So then I will just read off, right? I'll say if you read from x1, the next you write to x2, then to x1, then to x2, until you are finished with that particular thing. And then you know, okay, you know the parity of the variable you have finished reading, writing. So the next guess comes, it will start on the next variable. The
So
other
you're saying that two variables are sufficient for the reduction.
Actually, no, I have x1, x2, x3, x4.
For the other three.
y1, yeah, exactly.
Okay.
So yeah, I need like 4 plus 2. These many variables are needed. I have also some local registers which I am not counting here. Okay, I am not showing the gory reduction, I am just trying to give the idea here. And now what P4 is supposed to do, let's say, so P4 is the guy who's checking whether the words formed are actually the same. Okay, P3 does the same thing for the indices, which I am not going to look into. So what P4 is doing, now remember, P1 and P2 are writers. P4 is a reader. Okay, now remember the RA semantics. A reader. So when P4 begins, it is free to basically read anything it wants, right? The first time I'm saying P4 read from x1 and x3 and compare they are the same. Okay, here I'm showing good behavior. Okay, it read the first value written by P1 to x1. It reads the first value written by x3. Okay, and they are the same. Okay, so it says very good. First writes are matching. And then, okay, it can also say, it can behave well for some more time. It can say, okay, the next ones are also matching. But there is no guarantee that it has to, read exactly in the order in which the writes were made, right? Because RA allows me to jump to a later timestamp than my current timestamp, right? So, fine. For a while, it is doing good. But then, it can also cheat. For example, you can do this and falsely announce that it matches when it does not actually, right?
Yeah. No, I couldn't follow that part. Like where you were saying that it can cheat.
It can cheat in the sense, okay, so now if you were P4, you were supposed to, okay, so till here they are doing good, right? Till this blue and blue is okay. Now I'm supposed to read this blue with this blue, right? Because that was the order in which the writes happened.
Exactly.
But this guy did not do that. Okay, he just went ahead and read these two and said they are same.
Oh.
The reason being, he's a reader. And his timestamps corresponding to x1, x2, x3, x4, okay, it's at this level. So this whole world is open to him, right? There's nobody to kind of constrain him and say that, hey, you cannot just jump, but he can jump. Okay, so this is just to say that, there is a problem in this reduction, which is inherent to RA with reads and writes. So, okay, if it was sequential consistency, then I don't have the problem of jumping. But then sequential consistency is not on this side. So there the problem is because, okay, if you have to do this under sequential consistency, how would you do it, right? So remember in SE, the problem is you have to read the last value written. So every time you write something, you have to immediately read it. Okay. Now, when you do that, you have to also keep in track the indices also. Now, I don't know how long my, U1 and how short my V1 is. Maybe U1 is like 20 symbols long and V1 is 1. Okay, so somehow I will die in the process, right? I cannot just keep remembering these lags that I'm creating between UIs and VX because I'm always reading the last value written. So in SC, somehow this doesn't work. Whereas in RA, I don't need to kind of, remember anything because I'm allowed to, whatever, jump, but I am not supposed to jump. So the question is, how do I constrain this guy and actually show that the checking process actually checks exactly the way they were written without jumping over anything. That is the real question. Okay, so P4 jumps and cheats, very good. Okay, so now I'm just trying to put a bit more perspective into this by putting the timestamps also on the side. So T1 to T7 represent the timestamp that were chosen when these writes happened to X1, X2 respectively. And T1 prime to T7 prime are the timestamps that were chosen when these writes happened in T2. Okay. So now let's see, this is just to see how the view changes. Okay, so when P4 begins, the view is all 0 because it has not written anything, it has not read anything, so it's all zeros. And now the first time P4 reads, let us say that it is reading from the first value, it's written just by chance, okay? Not that it was compelled to, just by chance. So I need to also ensure that the first time the checking starts, it has to check from the first value written. I'm not doing that here, I'm just trying to show that how the view changes. Just so that we appreciate what happens when a jump happens and how we can catch it. Okay? So here it reads well behaved. So timestamp of x1, x3 progresses. Notice that x2, x4 is unchanged because when this write happened, x2 timestamp was 0. When this write happened, x4 timestamp was 0 because those were the first ones. Now, okay, it does the next one. So very good. Okay, so fine. This is what happens. x1, x3 timestamps do not change. Now notice that if it jumps and goes ahead like this, indeed I do get x2, x4 timestamps as T4, T4 prime, but notice that when this write happened, this had already happened, which means in my view, when I inherit T4, I will also inherit T3 when I read it. Which means when I actually do this, my timestamps would look like this, which means I've changed all my timestamps here when I jump. Okay, this is something to keep in mind, because this can potentially help us in controlling this jump if we use the atomic read-write operation. Okay, which is why I said I don't know the status of the problem. If I have just reads and writes, then open problem till date. But with atomic read-write, I can potentially do something so that I can stop the process from jump. So let's see how we can do that. That is the slide, and this is the last slide of undecided. Okay, so once again, this is how I am at the moment. So I'm going to start with the initial value being a black color for all the 4 variables. Okay, and these are the colors coming from the PCB problem. So black is a color which is a fresh color which does not figure in the PCB alphabet. Okay, this is my assumption. So now when P4 begins, okay, its initial values were 0. So I'm going to first say that I'm going to behave. Okay, let's maybe I don't behave. So my first instruction says do an atomic read, right? So I'm reading the green one and rewriting it to black. Okay, so the semantics of atomic read-write says, can I read the green? I can, because my current timestamp was 0, T1 is higher, so I can read it. But then when I do this atomic read-write, I'm basically creating an extra write and my timestamp becomes T1 plus. Okay, so this is what happens when I just do this. Now, I also do one more thing at the end of this. Okay, I'm going to say read the x2 black. So I'm basically creating a couple of instructions each time. So I'm not yet compared with x3. I'm supposed to do that. But this is what I'm going to do. So is this read possible? Can I read x2 black? I can. Because my timestamp of x2 is 0 and the initial value written is black. The timestamp is 0, so I can definitely read that. So right now it goes through, no problem so far. Now I'm going to check whether x3, the initial value of x3 is also read. Okay, that's what I'm supposed to do. Okay, so here the way the slide will show it, it will do it properly, in the sense I'm not cheating right now, but we can already think what happens if I had to cheat, okay? So I'm saying, okay, can you read x3 green? I can, because my current timestamp is 0 and this one is T1 prime larger than 0, so I can read it and I'm doing the atomic read, right? So I'm overwriting it black, which means my view becomes T1 prime plus 1. And now at this point, I'm saying read x4 black, okay? At this point, I can because my timestamp is 0 and I have the initial black. So assume for a moment, okay, that when I try to check x3 green, the process tried to read this. It could have done that, right? Because that was green, it's also an x3. So instead of reading this one, suppose it read this x3 value, then what would have happened? Then this view, when it read this value of x3, this T1 prime would have been T5 prime. But then it would have inherited this T4 prime of x4, okay, because that write happened before this, right? So the view would have become x4 would have been T4 prime, this would have become T5 prime, okay? And now when I say read x4 black, what is my timestamp of x4? T5, right? No, T4 prime. Do I have a black which is possible to be read from? The only black I know is here, whose timestamp is 0, which means to begin with, if I cheated by going down, I would have died here. I would not be able to read x4 black. So this is how we can stop the initial cheating. So at least to start with, I have to read the initial values written by both parties on x1 and x3 respectively. So that is where this atomic rewrite is really helping me. And this read coupled also, they are kind of behaving as a pair so that it does not allow me to jump. So to begin, this guy cannot jump. It has to start from the first one. Okay, now I think I have a couple of good reads. What is happening? Something happening.
Search those.
Okay. Okay, so now I'm going to behave. Okay, so fine. Yes, this here it is possible because I didn't cheat. I can read the initial black. So the next value is I'm going to behave well. Okay, I can read x2 red. Okay, I'm overwriting with black. Atomic read right, and now I'll say read x1 black, which is possible here. Why? Because the last time I wrote to x1 was through this atomic read right, and the timestamp happens to be t1 plus 1. I can read my own right. So here it is possible because I have not gone ahead and jumped. So yes, because of that, it happens. And now I'm going to check if x4 has read. Okay, because I'm trying to compare the second writes made by the two parties. I'm going to do the same thing. Okay, so there again, I've done no cheating. So when I now say read x3 black, it will again be successful. No worries. And now I think I will cheat already. Okay, this is my own right above. Okay, so that works fine. Let's see. Okay, here I'm cheating. Okay, here I'm jumping ahead. I'm supposed to have read this blue. But I know somehow that blue and red are not going to match. So I decided to cheat it because I know these are green somehow, okay, by some guess. So now when I do this atomic rewrite x1 green black, notice my view currently. So T5, it has inherited T4. These two guys remain unchanged because they are not part of this thread when I read from. And this is what it was. But now I'll say, okay, so after the atomic, the right part of it, T5 becomes T5 plus 1, that is fine. Now I'll say read x2 black according to my protocol. Now, can I do x2 black? Okay. So my view for x2 has become t4. But when was the last time I wrote x2 black? It was here. Okay. The timestamp basically at that time was just t2 plus 1. t2 plus is certainly smaller than t4. So this read will not become successful because it. So basically, yes. So because of this, we can control jumping, but with atomic read, right? Now, atomic read write is certainly a costly operation because it's doing an atomic operation. And I'm doing this somehow in every line of my constructed program, I'm having an atomic rewrite, almost every line of the program. So it's like a costly construction. And I don't know what the status is if I do not have atomic rewrite. All that we know is that it is non-primitive recursive. So we have a lower bound. We can simulate lossy channel systems. Lossy channel systems are quite intuitive because if I have just writes and reads, right, I can jump over writes, which is exactly what happens in a lossy channel system. Because I can lose messages randomly. So it's basically the analog of simulating lossy channels makes it non-primitive recursive without atomic read writes. So just reads and writes is still open. And decidability seems hard, but then we don't have an upper bound proof for this. We just have a lower bound. Okay, so this is bad news already that
so upper bound for which one?
So if I just have array with reads and writes without atomic read, I do not know whether the upper bound is also NPR, we don't know. I can just simulate lossy channel system that gives me the lower bound, but I am not able to do the other way around, nor am I able to show some decidable. Okay, so basically I don't know. So this is not good news because I'm trying to say that verifying programs under array is not easy. So what do? We don't give up. We go to standard well-known, or we look at the literature for standard well-known under approximations. So context-bounded analysis is a very well-known under approximation. So what happens in context-bounded analysis is that you do not look at all possible executions. So a context is basically a sequence of steps where the same process is kind of moving. Okay, that is one context. When the process changes, that is a switch of context. So if I say that, look at all executions where the context bounding is, let's say, 5. So I'm saying one process runs for a huge amount of time. Then there is a switch, another process takes over. So that's one switch. Like that, you can do up to 5 switches. Okay, so as an example here, so P1, P2 whole star has an unbounded context switch, obviously, because they are continuously alternating, but this is one context bounded, right? So this is a very well-known under approximation for sequential consistency. And we know that this NP complete for sequential consistency. Okay, if I just look at context bounded reachability, it's NP complete. And there are very successful tools which basically have implemented context boundedness. So can we do something similar for reset? So now the first attempt is to ask, can I do the same thing? Can I look at programs under release acquire where I look at context bounded runs, but then it doesn't happen because if we look at my construction, I could have just said, okay, P1 you write your guesses, done. P2 you write your guesses, done. P3 check, P4 check, right? So it's like 1, 2, 3 context switches is sufficient to get undecidability. So somehow the well-known under approximation does not work for release acquired. We need to propose something that is more appropriate for release acquired, the model of release acquired, so that it becomes a meaningful under approximation. And that leads us to what we call, yes, we need a different under approximation for array. So that leads us to something that we call view switching. So view is something very inherent to array, right? Each process has its local view. And the view changes when you kind of update your information. So maybe it is more relevant for array to say that let me look at how many times my view is switching in my entire execution. If that is bounded somehow, maybe it is a good under approximation. Of course, good or not, we have to see depending on the benchmarks. But perhaps it's a good under approximation. So if I look at this sample run, so let us decide what is a view switch, what is not a view switch. So a view switch happens when a process reads a value written by another process and changes its view. So notice that when I read what I wrote myself and change my view, it does not really change the view, right? Because I've written it, my view is already updated. When I read it myself, I'm not really changing my view. But typically when I read somebody else's write and update my view, that is a real view. So in this example, if I look at it, okay, the red process wrote a 1, and when this green process tries to read it, this is actually a view switch, right? Because the view of y increases. I'm writing y, I'm writing x, okay? So, this is a view switch, but this is not. Do we see that this is not a view switch? So when I read this, I have already inherited this timestamp of y. Therefore, when I read y3, I am not really changing my view. It's the same view. Right? So this is, so I have only 2 view switches. So this is an example of an execution with 2 view switches. Okay, so 2 bounded runs. So what we do is we following, okay, this is just to illustrate another concept needed in this under approximate reduction. So what we do is we are now going to bound the number of essential views in the memory. So I'm going to say that a view is essential. So each box is a view. So when we saw till now, the memory pool had unbounded number of views. But now I'm going to say that keep only those views which actually result in a view switch. So if I'm going to look at runs where the number of view switches is bounded by k, I'm basically making my memory pool finite. That's exactly what I'm doing. So I'm saying do not consider those views which are not going to be essential for you. Keep exactly those views which are kind of needed for a view switch. So this guy. It's a small problem here. The problem being, think of this view, okay? Y is 3. I can't just forget it like that. The reason being, somebody is actually reading that one. Okay? So I cannot really forget this. So we have to classify messages into 3 categories. Redundant, which means nobody is going to read it. The value is not needed. Those are redundant, so just throw them out. Now, this message is a useful message because somebody is actually reading it. And essential messages where the view switch actually happens. Okay, so I'm just going to do something so that if I have a useful message, the value gets somehow incorporated. Essential messages I'll just keep in my memory pool, and that's pretty much it. Okay, so the reduction we are proposing basically goes from up by 1. So it is not hard to notice that the undecidability proof we had actually required unbounded number of view switches. Right? Because every time I'm doing this atomic read, right? I'm basically continuously going ahead in my read, right? Every read was basically changing the view. So I could not have accommodated with a bounded number of views. And of course, I don't know how long is my PCP solution, right? So depends on that. So it's basically not bounded. So somehow, okay, this concept does not apply to the undecidability proof. So this is really an under approximation. So given this, this is the main result that I will restrict my reachability to k bounded runs. So here k bounded represents k view bounded. And the main result is that I will now reduce the k bounded view switch problem of array to the k plus n bounded context reachability on the receiver. N is the number of processes. So the idea roughly, okay, roughly the idea is the following. So if I say k is the number of view switches I'm interested in, So there are K essential messages generated by some guys. I don't know who did it. Okay, K messages are essential. So I will first run the processes so that those K messages get generated first. So once I have all my essential messages, now I'm not going to make any more switch. Then I'll run all the process one by one. Okay, so the maximum number of context switches I need to generate K essential uses K, followed by all the process one after the other. So K plus N would be the number of context switching when I sequentialize the program. Okay, so this is the idea roughly. And how much time do I have?
We are almost on this time.
Okay, that is fine. Okay, then I can wind up. I just need, okay, couple of slides again, just skip because the detail is not really so much important. So a K-bounded reachability is therefore decidable. Okay, so this is some detail on how the data structures were developed, okay, how it was implemented. So let's not go into that, it doesn't matter. What is interesting is to see the experimental results. So we implemented this view bounding. Okay, so we basically did the following. So we developed this model checker called view bounded model checker. So we did this code-to-code translation so that we get a corresponding program that is interpreted as a bounded context switch under sequential consistency. We used off-the-shelf tools which can do this analysis. And then we looked at all the known benchmarks. And what we realized is that if we compare with the classical model checkers, which do the trace analysis, we are actually able to detect bugs much quicker with this approach. So in some sense, view bounding works better than this classical decoy algorithms if there is a bug. On the contrary, if the program is not working, if it is a safe program, then we are not as good in saying there is no bug. Okay. So somehow I think this decoy algorithms, I think their heuristics are much better. They are much quicker in their exploration if there is no bug. But especially, if we place like a bug in some remote corner of the program, then we are doing much better than these guys. Okay, because somehow they still have to look at all possible traces, which we don't have. Okay, so that is the message. So this is a whatever under approximate analysis for race acquire. Now, other questions that are kind of very much open now is something called consistency checking for concurrent programs. So consistency checking basically is, now we saw the traces, right? We said that I will look at traces than concrete runs. So one question is, can you synthesize this RF and MO edges so that you can check that the corresponding trace is consistent? So this year at POPL, we had a paper where we looked at some variants of weak memory and established some complexity results for that. Most of them in NP complete, some of them, very few of them in polynomial time. Now, the reason why this is good is because in your model checker, checking whether the trace you have generated so far is consistent is an important step, right? Because you are building the trace, but it must be consistent with respect to your memory model so that you can do it. Okay, so this is like one of the follow-ups of this. Otherwise, I'm done. Thank you so much and sorry for the extra time.
Questions?
Since RA is more popular than sequential consistency?
Yes.
It is.
Yes. So actually, I just said array because, okay, this was one of my work. But if you look at, so there are these other models called ARM, Power. So IBM has Power, right?
Okay.
And Intel is implementing something called TSO. So these are all weak memory models, which are all different from sequential consistency. So in that sense, the argument to say it's practical is basically that all these modern architectures implement other things than sequential consistency. And RA is a reflection of, carrying those things by having primitives. So there's more at the programming language level, but, people who are working more with these processor architectures would appreciate if I do the same thing for Power, for example, right? I can say, given a program under Power, can you check the reachability problem? Likewise for Intel TSO, right? So that is why this is somehow practical.
I understand. Yeah, okay.
So as a
practical is
yeah. So as a programmer, when I'm writing a program, what I have in mind is sequential consistency, like as
I agree.
correctness.
I agree.
And now if you are using something which is different as an underlying memory model, then the program that I have written, which it might be a Baki program, but
Perfectly, exactly. Like as we saw in that store buffer example.
yeah. So then how is that taken care of? Like, because most of the time when I'm writing the program, I find that whatever I'm expecting.
So you
I see
basically
that.
want to
Without
make
my-
your program interpreted as RA to be interpreted as sequential consistency, right? So you want it to behave
No,
as it does only in sequential consistency.
Yeah, exactly.
So there is a technique for that. So it is called inserting a fence. Okay, so a fence is like waking up a sleeping person and say, go read the newspaper. Okay, I cannot pretend that, hey, I didn't get a phone call. So if I insert fences, what happens is your view becomes up to date with the latest one. So if at a certain instance, so for example, in this mutual exclusion, right, Fisher's mutual exclusion protocol, under RA it is buggy. Buggy in the sense, I can basically both can come in the critical section, but if I put a fence there, then both people will become aware that, okay, globally somebody has taken them.
So is it the programmer who is putting the fence or it's a compiler?
Yes. Typically, the programmer can put the fences. Now, inserting fence again a costly operation.
Yeah.
So one question that is very much relevant is, if you want to kind of make your program behave somewhat like sequential consistency in certain places, can you find the minimum number of fences to be inserted so that you get what you want? At the same time, keeping it more or less not so expensive.
I mean, but when we are doing our 101 programming course, I mean, we usually don't write programs with fences, but still the programs work correctly.
I agree. No, the problem is not that it doesn't work correctly. The problem is, this overhead of constantly talking to the memory, right? The performance decreases. In CS101, we are least bothered about how quickly a program runs. I'm more in touch with the program runs correctly. Right? 101 course, do we really worry about how quickly my program runs?
No, but the correctness is because of the compiler is doing some changes, like it is putting the fences.
Yes. So when you say correctness, you basically are looking for behavior which is sequentially consistent. Right? That is your notion of correctness.
Yeah.
So to achieve that, one way I can do is, right, you take an RA program. After every write, put a fence.
Yes.
Okay, if after every write you put a fence, you are basically forcing, this semantics to say that every time you make a write, okay, you go and sync with the global thing. So then when you read, you're always up to date. Everybody is up to date, right? You can do that. But then putting fences, so when you run such programs under these modern architectures, they are going to be much slower, right? Because every time you put a fence, it's like syncing. You're basically making it sequentially consistent.
Mm-hmm.
So, but if you know, for example, that at certain points, you want a sequentially consistent view, then you just put a fence at exactly those points. Pretty much. So if you want to detect a bug, it was there because of RA. Okay, but then you just put a fence. But then you should know how to minimally add fences so that you get what you want and the processor does not suffer much. That is pretty useful.
Shared memory is increasing. Did you have multi-threaded programs in mind?
Yes, I was talking about like the multi-threaded programs in mind. So I as a programmer, usually I don't write the fence instructions, but then when I'm running it on Intel processor.
You said 101, like most beginner.
The basic programming course we teach it already. The introduction to programming. That is CS101.
Yeah, there you wouldn't.
There, who cares about
threads? I don't know, I'm talking about threads. People writing two threads. Like a mutual exclusion kind of a thing.
Yeah.
Right, mutual exclusion some ways. Basic to it might have. But there you were writing different kinds of fence instructions.
Yeah. And then you interpret under these models also.
They are interpreting under, like, if I'm running on an Intel processor, it will be using this.
Sure, so you will get a different behavior.
Oh, we get it.
Yeah, of course, you do. Certainly.
Yeah,
You will get extra behaviors.
I see.
Absolutely.
Unless you tell them that you're in CS101 course and you want the
Okay. So we should go. I should go. Okay. Any other question? Okay, then let's thank Krishna again.